Hi everyone. So in this video we will discuss about one of those non-zero density setups that we said we can afford in QCD. And by we can afford, we mean that we can simulate in this setup by employing standard Monte Carlo techniques based on importance sampling. So the full partition function or the expectation value of any given observable can be written in a way that after having integrated out the fermionic fields, getting some power of the fermionic determinant, which depends on the flavor content of your theory, we are still in a position to include the power of the determinant in the Boltzmann weight without spoiling its reality and positivity. We mentioned already in the previous video that QCD at non-zero isospin density, so when we have correspondingly to the density a chemical potential which it's conjugated to the density of up minus the density of down quarks, can be simulated because there is no sign problem in that setup. And this is one of the applications that we will go through in this part of the class. As said, here we are in a setup which is dense, but sign problem free, and dense not in the sense of being baryon dense. So rather than there being an asymmetry in terms of how many particles versus antiparticles we have, there is an asymmetry in terms of how many up and down quarks we have, which gets reflected into an asymmetry between neutrons and protons or positively and negatively charged pions. Actually, the phase diagram for this setup, which then is in the plane of temperature and isospin chemical potential for QCD, was first drawn on the basis of some analytic calculation that have been proposed in this paper back in 2001. Of course, two limits had to be considered, which are the only limits where one can work out the phase diagram without resorting to numerical simulations. One of these two limits is the limit of zero density, which is where the absolute value of our chemical potential is much smaller than the mass of the raw particle. And this is where chiral perturbation theory applies. There we have the positively and negatively charged pions being the lightest hadrons that couple to mu I because they have the right quantum numbers. And chiral perturbation theory does describe their effective dynamics in a very effective way. What one can figure out by applying chiral perturbation theory in this setup is that at t equals 0, and for mu I being beyond the critical threshold, which in our notation is at half the pion mass, there is sufficiently energy being pumped into the system such that pions can be created. Now, what is the peculiar feature here? That the lightest hadrons coupling to isospin are pions which are bosons, and differently from the baryons that couple to the quark chemical potential in the T versus baryon chemical potential plane. And so what happens here is that a Bose-Einstein condensate of these pions is formed, which in the plot is indicated by expectation value of pi minus different from 0. Yes, and the hadronic or BEC phase transition, so here you have hadronic and here you have Bose-Einstein condensate phase with the pion condensation, the line, the boundary that connects the two phases, is predicted already by chiral perturbation theory to be second order. And this was also checked on the lattice that it is indeed a second order phase transition and in the O2 universality class. There was another limit that could be tackled analytically for this phase diagram, and this is the limit of infinitely dense system, where the isospin density is sent to infinity, and that corresponds to a value of the isospin chemical potential, which is much larger than lambda QCD. I'm writing the modulus of the chemical potential because one can, in principle, have more down quarks than up quarks or vice versa, and still this corresponds to a non-zero density. In this limit, perturbative QCD applies. So you can run some perturbative calculation. You find out that there is a weak attractive gluon interaction that happens between quarks which are near the Fermi surface. And then what happens is that these form pseudoscalar up and anti-down, depending on the sign of mu I. This could be the other way around, Cooper pairs. So what happens is that Bardeen-Cooper-Schrieffer gap develops for sufficiently large values of mu I due to this attractive gluon interaction between quarks which are close to the Fermi surface. And then there is a phase transition also that connects the Bose-Einstein condensation phase with pion condensation to this other superconducting phase. And we should ask ourselves whether the phase boundary that separates these two phases should or should not be a true phase transition. For that, it is illuminating to look at what are the symmetry breaking patterns on the two sides of the transition, that is in the two different phases. And one actually finds out that the quantum number of the pion condensate is the same quantum number as this condensate of up and anti-down or anti-up and down, again, depends on the sign of the chemical potential, Cooper pairs in the pseudoscalar channel, which is why there is a gamma 5 here sandwiched in between. And this fact that the quantum numbers of the condensates are the same reflects the fact that the symmetry breaking patterns are the same in the two cases. And when this happens, then it is reasonable, and it was indeed conjectured, that the boundary is not a true phase transition, but rather a smooth crossover between the two phases. And then there is one last point, which will not play a big role here, but at asymptotically, at even larger values of the isospin chemical potential, the gluonic sector decouples completely. And if that happens, then this is effectively similar to pure gauge. And we know that in that case, a first order deconfinement phase transition is to be expected. And therefore, you have this first order line that then must end somewhere because this decoupling is only effectively there at very, very large values of the chemical potential. As we already mentioned them, and they are so important because they help us developing an intuition of how we should simulate the theory and what we should expect on the structure of the phase diagram, let's talk symmetry breaking patterns. So we need to start from the symmetry group of QCD, where we have some light degenerate pair of fermions, so with light quark matrix MUD that is given by this expression, where there is a non-zero mass for the two light species that are collected in a doublet. So this is the fermion matrix in the basis of the up and down quarks. Okay, so it contains on the diagonal the individual Dirac operators for the individual flavors. Okay, so it really looks like it's written in the formula over here. And in this setup, we have studied it already when we discussed chiral symmetry as a fundamental symmetry of QCD, which is broken at a small temperature and gets restored at the deconfinement, at the chiral restoration temperature, I should say. Then the symmetry group is the SU2 vectorial times the U1 vectorial, with the last one corresponding to baryon number conservation. All right, then we want to switch on some isospin chemical potential. And again, I could stay here and discuss with you how is this implemented. However, I have it already written down in this formula that the way you couple the isospin chemical potential in this basis that I mentioned before is you have mu I, gamma 4, tau 3, where tau 3 is the Pauli matrix, okay? And this is how you couple the chemical potential at the level of the big fermion matrix that describes the two flavors. Okay, but this has an impact on the symmetry group. Specifically, it breaks it down. And it breaks it down to u tau 31 times u vectorial 1. So if we want to think about how the potential looks like in this setup, and if you would put the other two Pauli matrices on the axis of a three-dimensional plot and plot the potential, then this u tau 31 would correspond to the blue circle. Basically, what we have at non-zero isospin chemical potential is a spontaneous breaking with some non-zero value of the pion condensate, which is nothing but the location of the circle on either of the two axes of this plot. And the fact that we can have excitations that can sort of loop around the Mexican hat is telling us that we have Goldstone mode. We have a Goldstone mode in this setup. That's bad news for us, because whenever there is a Goldstone mode, then the Dirac operator develops zero modes, and this makes it very, very hard to simulate this theory, where we have to invert the Dirac operator in the course of our Monte Carlo simulation. Therefore, we cannot stop here and go ahead and simulate the theory with non-zero isospin chemical potential. We should rather take into account another term at the level of the fermion matrix, which enters with a coupling lambda different from zero, which is called the pionic source, and it is coupled with an imaginary units and then gamma 5 tau 2. Remember, these are the Pauli matrices, so there is some combination of I factors over here. What is this term doing? This term is sort of explicitly breaking the symmetry further down to the empty set times uv1. So we have really broken down the symmetry completely via this explicit breaking through the pionic source lambda. And this makes the Goldstone mode a pseudo-Goldstone boson. So it is infrared regulating our setup, our theory. And it is also the necessary trigger for us to observe spontaneous breaking in finite volumes. All right, I think at this point we can think of what we just said about a setup with non-zero isospin density and compare to another setup that we have touched already when we were discussing non-zero temperature and zero density. In particular, we noticed that this breaking of the u tau 31 symmetry, which is achieved explicitly by a non-zero lambda, but that is also the result of a spontaneous breaking, if I go back one slide, of the symmetry that you get by setting a non-zero isospin chemical potential, is fully analogous to the breaking of the standard chiral symmetry in a setup in which you have zero density and a non-zero temperature. In that case, the spontaneous breaking of the symmetry at low temperatures is signaled by a non-zero value of the chiral condensate. And on top of that, since your light quarks have a non-zero mass, the masses are enforcing an explicit breaking of that same symmetry. So it is really such that one can write down a dictionary between these two cases. And on one side, you have the chiral symmetry breaking at low temperature in QCD at zero density. And on the other side, you have pion condensation, which corresponds to the spontaneous breaking of the u tau 31 symmetry due to the presence of a non-zero isospin chemical potential. The breaking patterns are different. In one case, you have the breaking corresponding to what's happening to this symmetry, and in the other case, you have the breaking of SU2 left, SU2 right to SU2 vectorial. And the other important difference is that you have, on the one hand, just one Goldstone, which is made pseudo by the fact that there is also an explicit breaking, which is what makes the symmetry group empty. And on the other case, in the other case, you have 3 pseudo-Goldstone bosons. As you know, these are the 3 pions, the neutral and the 2 charged ones. The condensates are matched in the way that I already described, and the explicit breaking are either by the mass or by lambda. And one last very important bit in this analogy is the fact that one can work out a Banks-Kasher-like relation also in the setup at non-zero isospin density, pretty much as in the setup at 0 density. We will discuss this in a moment, and connect this to the breaking of the corresponding symmetries and to the corresponding condensates, the chiral condensate and the pion condensate. Okay, one important point, though, about this analogy is also the fact that one needs to keep in mind that it is actually the fact that in nature we do have non-zero masses for the light quarks. These are physical parameters of QCD, while the lambda is just a trigger that we have implemented in order to observe this spontaneous symmetry breaking and to infrared regulate the theory. So in the case of the pion condensation and in the non-zero isospin setup, one needs to then take the lambda to 0 limit in order to recover physics as we know it. Okay, I mentioned this already in the previous video, but I think it is useful to see explicitly outcomes that we have no sign problem in such a setup. And this is based on an investigation that was conducted with staggered fermions that you have already heard about in this school. So this is the partition function. You see there is some fractional power of this large light fermion matrix that contains the individual flavor Dirac operators and the masses which are degenerate on the diagonal block. And the lambda, you remember the way it was coupled with this term in a way that it is proportional to tau2, and this means that it goes off diagonal. And of course, as said, this factor of I is cancelled. And eta 5 makes its appearance in place of gamma 5 because we are in a staggered setup. Okay, so you have 2 different fermion matrices. One is the strange fermion matrix. There is no chemical potential associated to the strange quark in this investigation and in the setup that we are discussing today. And the 2 light fermion flavors have isospin chemical potential. So they both have a non-zero mu I, and each of those get it with a different sign. All right, then the fact that the determinant for the strange sector is okay, real and positive, and we can simulate that, comes directly from the eta 5 hermiticity, which is the staggered equivalent of the gamma 5 hermiticity. And here I'm just reminding you what that eta 5 stands for. And when it comes to the light sectors, in order to prove that we have reality and positivity, we need to count on 2 properties. One of these is the staggered equivalent of chiral symmetry, which in formula reads like that. And the other is the modified eta 5 hermiticity, in the same sense as we have discussed about the gamma 5 hermiticity in continuum language when we would be switching on a quark chemical potential. Now, these 2 things taken together ensure that the light fermion matrix in the up and down basis respects a tau 1 eta 5 hermiticity relation of this type. And then you remember the argument in the paper by Alford et al. That if we can find out a matrix which is invertible such that we can write B M B minus 1 in a diagonal form where on the 2 blocks you have the Dirac operator and it's daggered, then you are done because the determinant of this block matrix would be real and positive. And this is what's happening here. You don't see the B minus 1 but the B because this matrix is its own inverse and it also has unit determinants. So when you then compute the determinant of the transformed matrix, this is just the determinant of this matrix. And you see that you have to multiply the two elements on the main diagonal, which gives you a modulus of something, so something positive. And you also have the off diagonal with a minus sign in front, which is plus lambda to the power of 2, which is certainly a positive quantity. And you end up then with a real and positive quantity. So this is like worked out more in detail, the proof of the fact that we really do not have sign problem in this setup. And then, as usual, when we want to study, for example, the phase diagram in one given setup, we need to identify the observables that it is interesting to look at in order to locate the phase transitions and, in principle, also do a finite size scaling analysis and establish the order of the phase transition. In this setup, it is natural to consider both the chiral condensate that we have already discussed for the mu for the zero density setup, and the pion condensate, which is characteristic of this Bose-Einstein condensed phase. Okay, now one tricky bit that I did not mention when we discussed non-zero temperature and the zero chemical potential setup is that it is not true that you have the chiral condensate measured like the Polyakov loop, that after your simulation you have one column with a value of the chiral condensate for every trajectory like you have for gauge observables like the Polyakov loop. What one actually does is one writes down the derivatives in this form, and then traces of inverses of Dirac operators appear. And these are complicated observables. If you would want to do this computation exactly, you would have to consider 12 times number of sites you have in your volumes propagator, which would be very difficult. And this is why I'm mentioning here that these quantities are measurable with noisy estimator techniques, okay? Just so you know it, and then we can discuss about this. Not only, but you also have to take care that you have correctly renormalized your the observables you want to look at. And in particular, this condensate renormalize either just multiplicatively, like the pion condensate, and then you need to take care of the multiplicative renormalization, which is done by this factor in front. In the case of the chiral condensate, you also have an additive renormalization that you can get rid of because this is independent of the temperature and the chemical potential. So what you do is you run also a zero temperature simulation and you make a subtraction. And then the +1 is just for normalization purposes. Okay, it makes sense to also look at the Polyakov loop, even though we know that strictly speaking, this is a good order parameter only in the limit of infinitely heavy quarks. And here we will be looking at results that come from a simulation where the quarks have their own physical masses. But nevertheless, it can be interesting for reasons that I'm going to explain in a moment. And here I have on the slides also the formula for the renormalized Polyakov loop. In this case, you also have a multiplicative constant that you can build by choosing arbitrarily values for T star and P star, which corresponds to each other. Different choices corresponds to different renormalization schemes, and in the for the results that I will show you later, this was the choice. And the rest is the usual Polyakov loop definition. Okay, and there is one more subject that we need to touch because we want to really construct this piece of the analogy that I mentioned before, that one can build a Banks-Kasher relation for this setup. So how is that done? One has to look at the eigenvalue equations for the Dirac operator, for example, d slash mu I, the massive one, so you also have the mass. And one can do that in the up sector, where the chemical potential is mu I. One can do that in the down sector, where the chemical potential is minus mu I. And in my notation, the psi tilde takes a gamma 5 in front. And then you observe that you can construct two eigenvalue equations that are matched by the conditions of eta 5 hermiticity and chiral symmetry. And then you look at them and you make the further observations that since D and D dagger do not commute, this is telling us that the left and right eigenvectors of this operator will not coincide. However, this relation between the two sectors is also telling us that for every eigenvalue in the up sector, I will have the corresponding complex conjugate appearing as an eigenvalue in the down sector. Then this means that we can also construct an admission operator, and this can be done by taking the modulus squared of the massive Dirac operator, in which case we would be considering a different eigenproblem, and this different eigenproblem would take exactly this form. So again, you have a set of eigenstates, which I am indicating by phi n, and you have this psi n square, which are the square of what we call singular eigenvalues. Okay, so the square root of these are the singular eigenvalues, and these are the eigenvalues of the eigenproblem that one constructs by taking the massive Dirac operator, daggering it, and multiplying it by itself. Can we do something out of this singular values representation for the massive Dirac operator that we have worked out? The answer is yes. We can work out, in analogy to the construction that led to the connection between the chiral condensate and the Dirac spectral density around zero, a Banks-Kasher type relation for lambda that goes to zero. For that, you basically consider the singular value representation of the pion condensate. So we already had given the definition of the pion condensate as the lambda derivative of the logarithm of z, and this then can be worked out and put in this form. And then we start from this form, and on the basis of the fact that this modulus square is diagonal in the basis of the eigenvalues, of the eigenstates for the eigenproblem for precisely this operator, then we can write down the spectral representation. And you might remember from what we said at 0 mu that next you have to take two limits, the v to infinity and the lambda to 0 limit, in which case you end up with pi over 4 times the expectation value of rho at 0. So similarly to what you have seen happening at mu equals 0 in the derivation of the ordinary Banks-Kasher relation, in this step over here, from here to there, the volume has been considered to be large enough, which makes the singular values become sufficiently dense. And this allows us to replace the sum with an integral upon introduction of what I wrote down here, which is the density of singular values. And other than that, we also observe that, like in the mu equals 0 case, the lambda to 0 limit leads to basically here to a representation of the Dirac delta function, and therefore we get to the final result, which is telling us that a non-zero pion condensate is equivalent to having an accumulation of near zero singular values of the massive Dirac operator. Then I would say, well, there are many technicalities that I don't cover in this video that have to do with the necessity to take the lambda to 0 limit after having introduced the pionic source in our setup. I still want to show you some results of what can be obtained concerning the phase diagram in this theory. In particular, we have different simulations that are run at different values of the temporal extent in the lattice spacing. In this way, one is in a position to start taking a continuum limit for a that goes to 0, that is larger and larger values of n tau. And one can look at the two observables that we have introduced, specifically the pion condensate and the quark condensate, and look in the two cases for different signatures that tell us where do we cross the boundary connecting the different phases in the phase diagram. In particular, one looks at the onset of the pion condensate, and by that one can locate the Bose-Einstein condensate boundary For example, in a plot where you have the temperature this time on the x-axis and the critical value of the isospin chemical potential divided by m pi on the y-axis. And basically, if the temperature is large enough, the pion condensate is always 0. Otherwise, at some values of the chemical potential, there is an onset from sigma pi to 0 to sigma pi different from 0. And there are interesting ways that one can take this continuum limit, which are described also in the slide. When it comes to looking at the quark condensate, one looks for the inflection point in the chiral condensate as a function of the temperature, now with reversed axis, and performing polynomial kind of extrapolations to the continuum limit, one can get the shaded orange area, which is the result in the continuum limit. And with this combined, one is really able to map out the phase diagram in the temperature versus isospin chemical potential over m pi plane. And then you have the onset of pion condensation at 0 temperature happening exactly at 0.5 in this convention for the units. I remind you that this has been done for 2+1 improved dynamical staggered quarks with physical quark masses. And you can see that this phase diagram has interesting features. This boundary is basically vertical up to 140 MeV, and then it becomes very flat at large mu I. And the chiral crossover basically goes into the other boundary, and starting at what we know, it's the temperature of the chiral crossover at mu equals 0. As I said, the complicated part of this project is the lambda to 0 extrapolations, which I don't cover in this discussion. I would rather try to convince you that it is interesting to still look at this phase diagram, because at this point you might be asking, okay, hadn't you told us that there should be also a superconducting Bardeen-Cooper-Schrieffer phase in this phase diagram? And the answer is that while that is conjectured, for the arguments that I have mentioned in the beginning that predict a superfluid state of up and anti-down Cooper pairs at very large values of the chemical potential and t equals 0, because the analytic argument works at t equals 0. And this is plausibly connected by a crossover to the BEC phase. Still, there is no numerical evidence for that, other than one can sort of interpret what happens to the Polyakov loops inside the BEC phase as an hint of the fact that one can have effectively deconfined constituents and at the same time Bose-Einstein condensation. And this is what one can read out of this plot that contains the isolines for the Polyakov loops. So the Polyakov loops have constant values within errors along lines of a given color. And in particular, the value of 1 corresponds to the deconfinement temperature at t equals 0. And you can see that this isoline basically penetrates the pion condensed phase. And then one can conjecture that the crossover, the BEC BCS crossover that we would be interested in if we want to figure out where is the other phase located in the phase diagram, might be just this same line that connects into the BEC phase. Just because the T deconfinement is insensitive to the boundary and you have large Polyakov loops in the Bose-Einstein condensate phase. So what happens? You make this conjecture in the form of a sketch and you say, okay, on one hand I have tightly bound pions and on the other hand I have weakly bound Cooper pairs, same quantum numbers, same breaking patterns, then there is a crossover. And one possibility or one option to look for that, which is actually current subject of research, and I am including it in the class, so just you see that there are ongoing applications of this, is that one can exploit what I mentioned to you already in the previous video as a generalization of the Banks-Kasher relation to sort of try and find out whether one can directly measure on the lattice the BCS gap that develops within the superconducting phase, just by looking at the complex spectral density. So this time it is really complex. We are not talking singular values, we are talking eigenvalues of the Dirac operator, and this can be accessed and measured on the lattice. This would be a video. It doesn't work here. Maybe I can play it during the class if we are curious to see how it happens that when the chemical potential grows, this basically spread this set of eigenvalues, which are along a vertical line in this plot. They spread in the plane and they encompass the value of the bare quark mass that you have given as input in your simulation, which is when the corresponding spectral density becomes non-zero. And this plot is there to indicate that this happens exactly, precisely at the BEC boundary. So there are interesting things, again, that can be told by a direct investigation of the Dirac spectrum, which is connected to what's happening in the chiral sector, even though in a way more complicated manner due to the fact that there is a non-zero value of the chemical potential. All right, and this brings me to the summary for this video. So I have discussed the theoretical motivations for studying QCD at non-zero isospin density. And I want to sort of iterate that again. It is conceptually and also technically similar with the case of non-vanishing baryon chemical potential, and the analogies are several. There is silver blaze phenomenon, so a transition from the vacuum to a phase with colorless composite particles in both cases, and in both cases the transition is accompanied by an accumulation of near zero Dirac eigenmodes, and then we have an ill-conditioned inversion that we need to take care of by introducing an infrared regulator in the theory. And the same technical similarity is also there with the chiral limit in the case of nu equals 0, as we have discussed in this analogy between pion condensation and chiral symmetry breaking. So the isospin chemical potential setup is basically a test bed. Also when it comes to studying superconducting phases at large densities, we saw that also in the isospin case, there are reasons to believe that there is one such phase at large values of the chemical potential, and it is currently under investigation. But if that's not enough, one also might want to think about the phenomenological motivation for studying this setup, which actually are also there. This is relevant for the early universe cosmology, as it has been worked out recently. There are circumstances under which it makes sense to think that the trajectory for the evolution of the early universe might have gone through the Bose-Einstein condensate phase with condensation of pions. And as usual in our simulation, the idea is that we can have full control over the parameters, and therefore effects that in nature are triggered by variation in just one parameter can be studied in the simulation. And in that case, one can say that the non-zero isospin density setup is relevant for studying isospin-driven effects in systems like heavy ion collisions as well as neutron stars. And that's it. So this is one of the types of densities that we can afford in a full QCD kind of setup. There is no sign problem. We can simulate there, and there is a lot of interesting physics questions to answer.